Hello friends, so today we are going to solve the questions from the chapter Heat and Thermodynamics, and we are going to solve the question from 2023, and in this we are going to solve 17 questions from the mains and 4 questions from advanced. So in totality we are going to solve 21 questions, and for the year 2023 this is our part 2. In the part 1 we solved question from the mains only, but in this part we are going to solve the question from mains as well as advanced, and this will be the last part of your 2023. In the next we are going to solve for 2022. So the first question: 1 gram of liquid is converted to vapor at 3 into 10 to the power 5 Pascal pressure. If 10% of heat supplied is used for increasing the volume by 1600 centimeter cube during this phase change, then increase in internal energy in the process will be. So in this case we have to find out the increase in internal energy, and it says that only the 10% of the heat supplied is used for, we can say, the increase in the volume, or we can also say that it is basically about the work done. Okay. So we are going to start with the work done. So you can say that work done during volume expansion suppose that is our W, which will be equal to P delta V, that is change in volume. P is our pressure, which is our 3 into 10 to the power 5, and change in volume is our 1600 centimeter cube. So we can say multiply by 1.6 into 10 to the power minus 3. Therefore from here we get that our work done is equal to 480 joules, and it says that only 10% of the heat is converted to the work. So we can use that since %% of heat, suppose that heat is given as Q, is used for work, and this statement can be written in the form of the equation that our 10% of Q will be giving us the work done, or we can say that our work done will be equal to 0.1 times Q, okay, and from here we can say that Q will be equal to our 480 multiplied by 10, giving us 4800 joules. So we found out the amount of heat. Now we can use our first law of thermodynamics. First law of thermodynamics, and we can say that our heat is equal to change in internal energy plus work done. We are supposed to find out the change in internal energy, that is delta of U will be equal to Q minus W. Q is our 4800 and W is our 480. Thus we get that the change in internal energy will be equal to 4320 joules, and option 1 is correct. Next question. It states that let gamma 1 be the ratio of molar specific heat at constant pressure and molar specific heat at constant volume of a monatomic gas, and gamma 2 be the similar ratio of diatomic gas. Considering diatomic gas molecule as a rigid rotator, the ratio of gamma 1 to gamma 2 is. So we are going to find out basically the ratio of their you can say adiabatic index, and we are given that gamma 1 is for our monatomic. So we can write this as gamma 1 is equal to constant pressure 1 and constant volume 1. Okay. And we know that for monatomic, our CV of 1 will be equal to 3/2 times R, and from here we can find out our Cp of 1 will be equal to Cv of 1 plus R. So we get this as 3/2 R plus R, giving us 5/2 times R. Therefore, we can say that our gamma 1 will be equal to 5/2 R, and we have this as 3/2 times R. Here 2 and R goes away, so we get this as 5/3. Similarly, we are going to write for our diatomic, and which is our gamma 2. So gamma 2 will be equal to Cp of 2 and Cv of 2, and it is said that we have diatomic, but the condition is given that it is a rigid rotator. It is a rigid rotator. So basically 3 translational and 2 rotational. So total degree of freedom will be 5. So based on this we can say that Cv of 2 will be equal to 5/2 times R, and Cp of 2, which is our Cv of 2 plus R, giving us 5/2 R plus R, which will be equal to 7/2 times R. Therefore, gamma 2 will be equal to 7/2 and 5/2. Here R, 2 and 2 cancels out. This comes as 7/5. And we need the ratio of gamma 1 to gamma 2. Therefore, we can say our ratio, which is gamma 1 upon gamma 2, will be equal to 5/3 and 7/5, which can be written as 5/3 and 5/7. This comes as our 25/7. 21. So we get 25/21. Option 3 is correct. Next question. It states that a Carnot engine with the efficiency 50% takes heat from the source at 600 Kelvin in order to increase the efficiency to 70%, keeping the temperature of the sink same. The new temperature of the source will be. So we can just draw an approximate figure for our this Carnot engine. So this is our source, and engine, and on the other side we are going to have a sink. Sometimes it is called as a reservoir. And this engine is going to do some work done, that is W. And so we have two cases, or rather we can say we are given that initial efficiency is 50%. Our source temperature is, let us suppose, T1, and our new efficiency, or we can say final efficiency, let's like new efficiency, is our 70%. And it says that the temperature of the sink is going to remain same. Okay, so the temperature of sink is, let us suppose, it is our T2. Okay, and it will be same for our initial efficiency as well as our new efficiency. And we know that for the Carnot efficiency or Carnot engine, we can write that our Carnot efficiency, that is nu is equal to 1 minus temperature of our sink divided by temperature of our source. So we can divide this formula into two parts. First, our initial case, and in this case, initial case, the efficiency was given as 50%, which comes 0.5, 1 minus temperature of the sink, which is our T2, temperature of source is our 600. Therefore, we get temperature of sink T2 will be equal to 300 Kelvin. Now we come to our new case. The efficiency is our 70%, so this is 0.7, 1 minus this is our T2, and let us call that our temperature of the source is T1 nu. Okay. And so T2 is, we just found out, so this comes as 1 minus 300 upon T1 nu, and from here we get that our 300 T1 nu will be equal to, and this will be 1 minus 0.7, that will be coming as 0.3, or we can say our T1 nu will be equal to 300 divided by 0.3, and this will be coming as our 1000 Kelvin. So new temperature will be 1000 Kelvin. Option 2 is correct. Next question. It states that a bowl filled with very hot soup cools from 98 degrees centigrade to 86 degrees centigrade in 2 minutes. When the room temperature is 22 degrees centigrade, how long it will take to cool down from 75 to 69 degree centigrade? Okay. So in this case, we can use simple our Newton's law of cooling, which states that the rate of cooling is proportional to average temperature difference. So we can use our Newton's law of cooling, and that states that rate of cooling is proportional to the average temperature difference. Average temperature difference. So we have two cases. First case, the temperature is varying from 98 to 86, and the second case, the temperature is varying from 75 to 69. Therefore, we can say that average temperature in first case, let us call this as T average 1 is equal to 98 plus 86 divided by 2. That will be coming as 92 degree centigrade. And the temperature difference will be equal to 98, that is our room temperature, 98 minus 22 is equal to 70 degree centigrade. And okay, so we can say that our cooling rate is equal to 98 minus 86 divided by 2, which will be coming as 12 divided by 2 and coming as 6 degree per centigrade per minute. Now we come to the second case. And for the second case, average temperature, let us call this as T average 2 will be equal to 75 plus 69 divided by 2, giving us 72 degrees centigrade. And the temperature difference will be equal to our 72 minus 22, giving us 50 degree centigrade. And we know that the time is inversely proportional to the temperature difference. You can see that our time is inversely proportional to temperature difference. It means time for second case ratio time of first case will be equal to temperature difference of first case and temperature difference of second case. Therefore, we can say that our T2 will be equal to our 2 into 70 upon 50, which will be giving us 2.8 minutes. Now the temperature changes from 75 to 69. You can say that our temperature changes from 75 to 69. This gives us 6 degree centigrade. Therefore, you can say that time taken for 6 degree drop, let us suppose that is our T, is equal to our 6 by 6 and divided by 50 and 70. 70 and 50, yeah. So this comes as our 1.4 minutes. So therefore, our answer is option number 2 is correct. Next question. According to law of equipartition of energy, the molar specific heat of a diatomic gas at constant volume where the molecule has one additional vibrational mode is. So it is being asked that the diatomic gas should be having one additional vibrational mode, and for that we are going to find out the molar specific heat at constant volume. So in general, we know that for diatomic gas, degrees of freedom there will be 2 degrees of freedom associated. First will be our transnational, which is our 3, and then we are going to have rotational, which is our 2, and then it is asking that it should be having one additional vibrational mode. So means we should be having a vibrational, and vibrational, it is said that it should be having one mode, and one mode basically means that independently it is going to have one for kinetic and one will be for potential. Therefore, the total will be equal to 1 plus 1, that is our 2. Now we can find out total degrees of freedom. Total degrees of freedom will be equal to 3 plus 2 plus 2 is equal to 7. And we have to find out the specific heat at constant volume. It means C of V is equal to F upon 2 times R. So this comes as 7 by 2 times R. So we have option number 4 is correct. Next question. It states that the graph between two temperature scales A and B is shown in figure. Between upper fixed point and the lower fixed point, there are 150 equal division on scale A and 100 on scale B. The relationship for the conversion between the two scales is given by. So basic graph is given to us. So we have temperature for A and temperature at B scale. Okay. And if you look closely, we can see, or it is rather given also, that our A is having a scale of 150. It means this will be our 30. Okay. And the B is going to have a minimum of, you can say, the lowest point scale of B will be equal to 0. So the lowest point scale of A is 30 and that of B is our 0 degree centigrade. Okay. This conclusion we can draw it from here, and therefore we can say this portion, small one, is our also 30. Okay. And so we can say that lowest point scale at A is our 30 degree centigrade, and okay, it's not mentioned 30 degree centigrade, so let's go for 30, and at B we have our 0 degree. Okay. And the highest point scale at A is our 180, and at B is our 100. So first of all, let's find out the range as well as the division size. Range and division size. So we have scale A, and for scale A, the lower point scale the lowest point scale is our 30, and the upper point scale is our 180. Therefore, its range will be equal to 180 minus 30, giving us 150 units. Okay, and from here we can find out each division on scale. Each division on scale will be equal to, we have this range, this is about 150, and total is given as 150, so this comes as 1 unit. Similarly, we can find out for B also. So we can say for scale B, and that will be also equal to 1, because the lowest is 0, highest is our 100. So each point division on scale B will be equal to 1 unit. So you can say our each division on scale will be equal to 100 minus 0 upon 100, giving us 1 unit. Okay. And okay, now let us draw a comparison, because we assume that it is a standard scale, which the lower scale is our 0 degree, let's call that ice point, upper is our 100, let us call this our steam point. So let us consider it as relate to a standard scale, which is about degree centigrade in this particular case. And for that, we assume that our lower point scale is 0 degree centigrade, which we can also call it as a ice point, and we have our upper point scale, let us call this our 100 degree centigrade, or we can call this our steam point. Once again, we are going to do it for scale A as well as scale B. So we can say for scale A, we have total number of division is 150 for scale A. Therefore, we can say 150 divisions corresponds to 100 degree centigrade. Corresponds to 100 degree centigrade. Therefore, each division will be equal to our 100/150, which comes as 2/3 degree centigrade. So for A, if the temperature is our T of A, one second. Yeah. So for A, if the temperature is TA, and the degree centigrade if the temperature is Tc, therefore we can write that temperature TA relates to Celsius Tc, and that is our TA minus 30 divided by the 180 and minus 30, and that will be Tc upon 100. And from here we get that our Tc will be equal to 2/3 TA minus 30, and this is for scale A. Similarly, we can write for scale B. For scale B, we know that our scale B is having 100 division. 100 division, it corresponds to 100 degrees centigrade. Therefore, each division will be our 100/100, giving us 1 degree centigrade. Therefore, we can write temperature TB relates to Celsius Tc, and we get this as our TB minus 0, 100 minus 0 is equal to Tc upon 100. So from here we get our Tc is equal to our TB. And so let us call this as equation number 1 and this as equation number 2. So you can say from 1 and 2, 1 and 2, we can write that our Tc is equal to 2/3 T of A minus 30, which is equal to our T of B, because Tc is equal to T of B. Therefore, we can say that temperature at our B is equal to 2/3 T of A minus 30. Now it is just part of our calculation. We can write, let's open it, or we can multiply it. Let's open it first. So this can be 2/3 T of A minus, we get this as our 30, 20, and we multiply the fraction by 150. Therefore, we get this as 150 T of B is equal to 150 and 50. This will be 100 T of A, and minus this will be equal to over 3000, and Okay, there is no need to solve this much. I think we already got the answer. So we get from here, this is our TA minus, okay, let me solve this, then we can easily. So it states that TB by so 1 second. So let me keep this as it is. So from here we get our TB is equal to 2 by 3 times TA minus of 20. Okay. And let us try to match this with our option. So we have this will be twice TA minus 60 oblique 3. Okay. And this is our TB. One second, let me solve it again. So I multiply it by 150, and from here we get that our 100 times TA is equal to 150 times TB plus 3000. And let me take the options one by one and we try to sort it out. So we have this as TA minus 180 divided by 100 and TA minus 180 TA minus 180 and divided by 100 is equal to TB upon 150. So this 0 goes by 0 and we get this as our TB is equal to we can write this as 15 upon 10 times TA and minus 180 times 15 divided by 10. Therefore we get that our TB is equal to 2 by 3 times TA minus 270. And let's check it with respect to our fixed points. So we have our T of A is equal to over 30 and T of B is equal to 0. Therefore we get this as 0 is equal to 3 by 2 times 30 minus 270, which will be coming as minus 225. Obviously this is incorrect. And for the upper point, we have TA is equal to 180 and TB is our 100. Therefore we get 100 is equal to 3 by 2 times 180 minus 270. And on the right side, this will be coming as 270 and this goes by about 90. So 270 and 270 will be 0. So this is also incorrect. And next option, that is our TB upon 180 is equal to TA minus 40 divided by 100. So from here we get our TB is equal to 9 by 5 times TA minus 72. And once again, for the two fixed points, we have our we have our TA is our 30 and TB is equal to 0. One second. TA is 30 and TB is 0. Yes. One second. I think I wrote it incorrectly. It is TA by 180. Yeah. So this is TA and this is TB. Now it is correct. TA and TB. So we substitute the values. We get this as TA is our 30, 9 by 5 times 0 and minus 72, which comes as minus of 72, so which is also incorrect. And for the upper part, we know that our TA is equal to 180 and our TB is equal to our 100. So this gives us our 100. 80 is equal to 9 by 5 times 100 minus 72, which comes as our 108. So this is also incorrect. And next option is our T of B upon 100 is equal to T of A minus 30 and divided by 150. TA upon 100. Yes. So from here we can write that our T of B is equal to 2 by 3 T of A minus 20. And let's check for the fixed points. Once again, we are having T of A is equal to 30 and T of B is equal to 0. So we get T of B is 0. So this is about 2 by 3 minus 30 minus 20. And this goes by 10. So 20 minus 20 is 0. So left side is equal to right side. So this is our correct. And for the second point, we have our TA is equal to 180 and our TB is equal to 100. So we get this as 100 is equal to 2 by 3 times 180 minus 20, and this goes by 60. So 120 minus 20 is equal to 100. So left side is equal to right side. So this is correct. So we can say this TB by 100, option number TB by 100, and TA minus 30, option B is correct. Option B is correct. It is little bit complicated, okay, and based on this, next question. It states that a bicycle tire is filled with air having pressure of 270 kilopascal at 27 degrees centigrade. The approximate pressure of the air in the tire when the temperature increases to 36 degrees centigrade. Okay. So in this case we can use Lucas law, and based on this we are going to get straightforward our answer. Okay. So you can say it is also called as a Lucas law, it is called as a Lusak's law, a little difficult for me to pronounce, and which gives us that our P1 upon T1 is equal to P2 upon T2, and we are supposed to find out our P2. Therefore we can say our P2 will be equal to P1 times T2 upon T1. I simply substitute the values, and it is 270 kilopascal, and we have T2, that is degree centigrade. So 36 degrees centigrade is going to give us 309 Kelvin, and 27 is going to give us 300. So this comes as 278 kilopascal approximately. So option 3 is correct. Next question. It states that a body cools from 60 degrees centigrade to 40 degrees centigrade in 6 minutes. If the temperature of the surrounding is 10 degrees centigrade, then after next 6 minutes its temperature will be. So in this case we can use the Newton's law of cooling, and that's based on our formula. So we can say our Newton's law of cooling, and the formula is given as our theta 1 minus theta 2 oblique time T is equal to alpha times their average and minus theta naught, that is our room temperature or temperature of the surrounding. And we can divide this according to the question. So we can say for our first case, we can write this as our 60 minus 40, time is given as 6 minutes, 1 second. Time is given as 6 minutes is equal to our alpha, and we have their average 60 plus 40 and surrounding is our 10 degree. Okay. And both the temperature are 6, sorry, the time is 6. Let me check whether it is time is both in same case, both cases. Yeah, they both have 6 minutes. Okay, so we can say we are going to get, this will be our 20 by 6 is equal to our alpha, and we get this as 50 minus 10 will be equal to our 40. 50 minus 10 will be equal to 40, and okay, let's keep it like this only. We can find out the ratio, and then we have a second case, and second case is our body cools from 60 to 40. Okay, it will be 40 minus T divided by 6, and we get this as our alpha, 40 plus T divided by 2 minus surrounding is our 10, and let's take the ratio. This is okay, let me solve a little bit. So this gives a 40 minus T upon 6 is equal to alpha, and okay, it will be same, doesn't matter. So we can see the ratio we get this as our 20 upon 6, 40 minus T upon 6 is equal to, we have this alpha times 40, and this comes alpha times 40 plus T divided by 2 minus 10, and here alpha 6 and 6 cancel out, and 2 we can take as LCM, so this will be coming as 40. Okay, now to a simple calculation, we are left with 20 upon 40 minus T is equal to, this is 40 and it comes as 40 plus T minus 20, and this is multiplied by 2. This comes as our 80, and it will be 20 plus T. Okay, this goes by 4, so we are left with 1 upon 40 minus T is equal to 4 upon 20 plus T. We cross multiply it, we get this as 20 plus T is equal to, we get this as 160 minus 40, and making it left right, we get this as 5T is equal to 40 minus T and this will be 160 minus 20, that is our 140. So we get T is equal to 140 divided by 5. So we get T is equal to 28 degree centigrade. So we get this as 28 degree centigrade. Next question. It states that heat energy of 180 kilojoule is given to ice of mass 600 gram at minus 12 degree centigrade. Specific heat of ice is 222.3 and this will be per Kelvin, and latent heat of ice is 336. Choose the correct answer from the given options. So we have to find out the final temperature of the system, okay, greater than, less than, and their ratio, okay. So in this case, basically we are interested in finding out the final state of the system. So first of all, the ice temperature will be raised from minus 12 degree centigrade to 0 degree centigrade, and then at 0 degree centigrade it is going to melt. Okay, so this is the basic process of our ice melting. So we can say heat to raise ice temperature from minus 12 degree centigrade to 0 degree centigrade. Let us call this as Q1, which will be equal to M small c and multiply by delta T. So this is about 0.6 and it is given as 4 times 2, 0.3, and the change in temperature is our 12. Therefore we get that our Q1 will be approximately equal to 15994.56 joules. Now second part, the heat to melt the ice. Heat to melt the ice, which we can also call as a latent heat. And that is our Q2, which will be equal to M multiplied by its latent heat. So we get our Q2 0.6 multiplied by 336 kilojoule. So 1, 2, 3, this will be coming as 201 and 600 joules. So therefore total heat required to melt the ice. Total heat required to melt ice, and let us suppose that is Q will be equal to Q1 plus Q2. So we get our Q is equal to 1599.4.56 plus 201,600, and that will be coming equal to as 217,594.56 joules. But the heat given, it is 184 kilojoule. Okay. Therefore, we can say that our heat given, which is our 184,000, is less than our Q, which is heat required, that is 217,594.56. So from here we can say not all ice melts. So ice doesn't melt completely. So we can say not all ice melts. So therefore option E cannot be correct because it states that final system is going to have only water only. This is incorrect because it is going to have some water as well as our ice. So let us find out how much the ice will be melted. So we say let mass of ice melted is m of m. Therefore we can write the equation that our 15,999.56 plus mass of melted multiplied by its latent is equal to total heat supplied. That is basically our conservation. Okay. So we have our, this is our Q1 and this we calculated Q2. We can call this as Q2 prime in order to differentiate from our Q2, and that is equal to total heat given. And from here we can find out our M, that the mass melted will be equal to 0.5 kg. And this melted, so it means mass of ice remaining will be equal to 0.6 minus 0.5 is giving us 0.1 kg. Therefore we can find out the ratio now. So we can say ratio of ice to water, and remaining ice is 0.1 and only this 0.5 is converted into water. So this comes as 0.5 giving us 1:5. And final temperature of the ice of the mixture will be equal to 0 degree centigrade, because the mixture is a combination of ice as well as water. So final temperature of the system will be 0 degree centigrade. It cannot be greater than 0 degree centigrade because some amount of ice is still not melted, and the ratio is 5:1. So option A and D are correct. So we can say option 1 is correct. Next question. It states that heat is given to an ideal gas in an isothermal process. Choose the correct answers from the options given below. So basically it is talking about isothermal process, so which basically means temperature is constant. So if temperature is constant, there is no change in internal energy. Therefore, option A and B are automatically incorrect. So one of the option C is the correct one. Okay. Then we can calculate our work done based on this discussion. Okay. So we can say that for isothermal process, we know that our change in temperature is equal to 0. Therefore, we can say that change in internal energy is equal to 0. Okay. Now we can use the first law of thermodynamics. And which gives us that our Q is equal to delta U plus W. Delta U 0, so we get our Q is equal to W. And since heat is supplied, okay, so we are given that heat is supplied or we can say our Q is greater than 0, which is our positive, so work done will be also greater than 0. So that will be also our positive, and this is by the gas. So the gas will do a positive work. Option D is correct. So C and D are correct. So option 4 is correct. Next question. It states that the correct relation between gamma, which is C of P, to C of V, the temperature T is. So it is quite straightforward. The formula is already given to us. So we are given that for ideal gas, the adiabatic ratio is equal to our C of P ratio C of V. And this, you can say, both the ratio is dependent upon degrees of freedom. Degrees of freedom, not temperature. Therefore, we can write that our gamma is proportional to T raised to power 0. So, option 2 is correct. Next question. It states that the pressure of gas changes linearly with volume from A to B as shown in the figure. If no heat is supplied or extracted from the gas, then change in internal energy of the gas will be. Okay. So no heat is extracted or taken, so this is basically an adiabatic process. In that, our Q or delta Q will be equal to 0. And so we are given no heat supplied or extracted. Therefore, we can say our delta of Q is equal to 0. And from first law, we can write that our delta of Q is equal to delta U plus W. Delta of Q is 0. Therefore, we can say that our delta of U is equal to minus of W, where W is the work done, and that is nothing but our area under the curve, and W will be equal to our, this is given in kilopascal, so this comes as 30 into 10 to the power 3 multiplied by 150 into 10 to the power minus 6, and this comes as our 4500 10 to the power minus 3, or okay, in terms of so this can be written as 4.5 joules. Okay. So option 4 is correct. Next question. It states that a hypothetical gas expands adiabatically such that its volume changes from 8 liters to 27 liters. If the ratio of final pressure of the gas to the initial pressure of a gas is 16/18:1, then the ratio C of P to C of V will be. So we are going to find out basically the adiabatic ratio. Okay. And so we know that our adiabatic index, that is our gamma, is equal to C of P upon C of P. And for adiabatic process, we know that our PV raised to power gamma is equal to constant. So we can divide this into initial and final. So we can say our P initial volume initial raised to power gamma is equal to P final volume final raised to power gamma. And from here we can write our P initial upon P final is equal to V final upon V initial whole raised to power gamma. And volume is given to us. Okay, both are given. We need to find out the ratio. So we have our volume change of gas is our 16/81. So this comes as 81 upon 16 and is equal to, and we have this comes as our 27 upon 8 whole raised to power gamma. And okay, so we can modify it, and this can be written as, this is over 3 and this will be over 2, and this will be coming as 3 raised to power 4 and 2 raised to power 4 is equal to, this will be also 2 and this will, this will be 3 and this will be 2, and we get this as a cube, and so this will be over 3 times gamma. So as per our exponent's law, we can say that our 4 is equal to 3 times gamma, giving us gamma is equal to 4/3. So option number 1 is correct. Next question. It states that heat energy of 735 joule is given to a diatomic gas, allowing the gas to expand at constant pressure. Each gas molecule rotates around an internal axis but do not oscillate. The increase in the internal energy of the gas will be. Okay, so we have to remember that there is only rotation and there is no oscillations. Okay. And we are having a diatomic gas. So you can say that we are given a diatomic gas and its degree of freedom, that is our F, will be equal to 5, which is our 3 for translational and 2 for our rotational. Therefore, we can write that our C of V will be equal to 5 by 2R and C of P will be equal to 7 upon 2 times R. And it is expanded at constant pressure. Therefore, we can say at constant pressure, our heat Q is equal to N C of P multiplied by delta of T. And our internal energy, that is our delta of U, will be equal to N C of V and multiplied by delta of T. So we take the ratio. So we can say our delta of U upon Q is equal to N C of V delta T and C of P delta T. Here N and delta T cancels out. This comes as C of V upon C of P, which we already know. Therefore, we get this delta U upon Q is equal to C of V is our 5 by 2 times R, C of P is 7 by 2 times R. 2 and R cancels out. So this comes as our 5 upon 7. And the heat given is given to us 735. Therefore, we get internal energy is equal to 5 upon 7 multiplied by 735. And this will be equal to our 525 joules. So we get option 1 is correct. Next question. It states that a sample of gas at temperature T is adiabatically expanded to double its volume. The work done by the gas in this process is given, gamma is 3 by 2. So we are having adiabatic process. We know that T V gamma minus 1 is equal to constant, and we are given that the final volume is equal to 2 times initial volume, and we can write the equation as T initial V initial gamma minus 1 is equal to T final V final gamma minus 1, and from here we can say our T final is equal to T initial, and we have this as our V initial upon V final gamma minus 1. So we can say our T final is equal to T initial is given as T, and we have our ratio is 1/2, and this comes as 3/2 minus 1. So let us call it T initial still. So we get this as our, this will be 1/2. So we get our T initial upon square root of 2. So final temperature will be equal to our initial temperature and its square root. And we have to find out the work done. So work done during adiabatic process. Work done is equal to our NR, and this is our T initial minus T final divided by gamma minus 1. And we simply substitute the values. We get this as our N times R, T initial minus T initial square root of 2, and this comes as 3/2 minus 1. And T initial we can take as common, so this comes as NR T initial, and this will be over square root of 2 minus 1, and denominator will be equal to 1/2. And this can be written as 2, we simply can multiply. One second. Okay, I missed 1 square root of 2. So we get this as about 2 RT square root of 2 minus 1, and this is about square root of 2. And we can just rationalize it. One second. Square root of 2 minus 1, square root down, 3/2, and this comes as 2. Okay. So we can just rationalize it, and this gives us 2RT upon, this will be coming as 2 now, and inside we multiply it, we get this as 2 minus square root of 2. This 2 and 2 cancels out, and now we get our answer, R of T, and this is 2 minus square root of 2. So we get this R of T, 2 minus square root of 2, option 4 is correct. Next question. It states that for 3 low density gases A, B and C, pressure versus temperature graphs are plotted while keeping at a constant volume as shown in the figure. The temperature corresponding to point K is, so we have to find out the temperature at this point K. Okay. So we are given that it is at constant volume. So we can say that we can use the ideal gas equation. Ideal gas, which gives us that PV is equal to nRT. Now it is given that our volume is also constant. Therefore, from here we can write our pressure is directly proportional to temperature, because N and R are already constant. So therefore we can say, because according to the graph, at this K point our value of pressure will be equal to 0. Okay. If value of pressure is equal to 0, then the value of temperature will be also equal to 0. Therefore we can say that at point K we have our pressure is equal to 0, which gives us that the temperature is also equal to 0, but the temperature is absolute, so this will be 0 Kelvin, and in terms of degree centigrade this will be minus 273 degree centigrade. So option 1 is correct. Next question. It states that a Carnot engine operating between two reservoirs has an efficiency of 1/3. When the temperature of cold reservoir is raised by x, its efficiency decreases to 1/6. The value of x is if the temperature of hot reservoir is 99 degree centigrade. So in this case we are having two conditions. One we can say initial, and another one we can call as a final. So we can say our initial efficiency is 1/3, and it is said that the temperature of hot reservoir is our 99 degree centigrade. So hot reservoir, that is our T2, is about 99 degree centigrade, or we can say this is 372 Kelvin. And our final efficiency, or let's call this new efficiency, is 1/6, and it says that the temperature of cold reservoir, cold is our sink, so we can say the sink temperature is raised by x. Sink temperature is raised by x. Okay. And so we can say that our initial efficiency, the temperature is T2, that is of reservoir, and here we can say that our temperature of our sink is T1. So this is our temperature of our sink initial, and new temperature of the sink is sink temperature raised by x. Therefore we can say that our new sink temperature new sink temperature, let us call this as our T1 prime, will be equal to T1 plus x. Now we can use our formula for our Carnot efficiency. So under initial condition, our efficiency initial will be equal to 1 minus our T1 upon T2, and initial is given as 1 by 3, so this comes as 1 by 3 is equal to 1 minus T2 is our 372. Therefore from here we get our T1 will be equal to, this will be coming as 1 minus 1 by 3, that will be 2 by 3. 2 by 3 multiplied by 372, which will be about 248 Kelvin. And so we can write from here that our new temperature, new sink temperature, which is our T1 prime, will be equal to T1 plus X. T1 we found out is our 248 plus X. Once again we can use the efficiency formula for our final. So we can say our new, let us call this as NF is equal to 1 minus, and we get this as T1 prime upon T2, which gives us 1 by 6 is equal to 1 minus 248 plus X, and T2 was our 372. So this comes as our 248 plus X divided by 372. It will be equal to 1 minus 1 by 6 will be equal to 5 by 6. So we get this as 248 plus X is equal to 5 by 6 multiplied by 372, and this will be coming equal to as 310. Therefore our X will be equal to 310 minus 248, which gives us that our X is equal to 62 Kelvin. So option 4 is correct. Next question. So this question, previous one all were from the mains, and this we start from now advanced. We are going to solve total 4 of advanced questions. So it states that 1 mole of ideal gas expands adiabatically from initial temperature state of Ta V0 to a final state of Tf 5 V0. Another mole of gas, same gas, expands isothermally from a different initial state Tb V0 to the same final state Tf 5 V0. The ratio of specific heats at constant pressure and the constant volume of this ideal state is gamma. What is the ratio of Ta to Tb? So let us first of all draw our process diagram, and which is basically our TV diagram. And so we have our temperature, volume, and it starts from A. So let us suppose this is our A state and expands adiabatically to Ta and to Tf. Okay, so it starts adiabatically like this, and let us suppose this is our state B. A is having our Ta and V0, and B is having S. Tf and 5 V0. And another mole of the same gas expands isothermally, okay, expands isothermally, and initial state TbV0. Okay, so the volume is going to remain same. So this is our V0, so it is going to start from somewhere here, because final state is isothermal expansion, so it expands to this position. Okay, so this is our T naught. One second. From a different state, TB. Okay, so this is not B. One second. TA to final state. Okay, let me write this as simple state F, final state TF. Okay, and isothermally from a different state B. So this is our different state B. And here for state B, this is TB and V naught. So we have this is TB and V naught. Final state for both is same. So this is basically our TB diagram. And this volume will be 5 times V naught. Okay. So we can write this in terms of equation also. So we have adiabatic and this adiabatic is from A to F, and it can be written as our PA, V naught, temperature is TA. Okay, so we can write this as our PA, V naught, TA, and this goes to our PF, and temperature is, volume is our 5 V naught and temperature is our TF. And then we have our isothermal. Isothermal is from B to a final, and pressure is our PB and volume is our same and temperature is our TB. Final pressure is our PF, volume is our 5 V naught and temperature is our TB because it is isothermal. Okay. Now we can find out the relationship. So we can say for adiabatic, we can write that our PB, sorry, for adiabatic is PA and V naught raised to power gamma is equal to PF 5 times V naught raised to power gamma. Therefore, from here we can write that our PF is equal to our PA V naught upon 5 V naught whole raised to power gamma, which comes as PA, and this V naught and V naught cancels out. So this comes as 5 raised to power minus of gamma. And now we come our isothermal. Isothermal, we can write that our PB V naught is equal to PF 5 times V naught, and V naught and V naught goes away. Therefore, we get our PV is equal to 5 times PF or we can say our pressure final is equal to PB upon 5. And we can equate our, let us call this equation number 1 and equation number 2. From 1 and 2, we can write that our PA 5 raised to power minus gamma is equal to PB divided by 5. So we get from here that our PA is equal to PB and 5 raised to power 1 minus gamma. Now we can use our ideal gas law. Ideal gas law, and which is our PV is equal to nRT. And for isothermal, we know for isothermal, temperature at B is nothing but temperature at final F. And for adiabatic, we can write this as our T of A V naught gamma minus 1 is equal to T of F 5 V naught gamma minus 1. And this can be written as that T of F will be equal to T of A 5 1 minus gamma. And we know that our T of B is equal to T of F. Therefore, we can write this as our T of B is equal to T of A 5 raised to power 1 minus gamma. Therefore, their ratio, which is our T of A upon T of B, is equal to 5 raised to power gamma minus 1. Raised to power gamma minus 1. Option A is correct. A is correct. Next question. It was also asked in the advanced 2023. It states that a closed container contains a homogeneous mixture of 2 moles of ideal monatomic gas gamma 5 by 3 and 1 mole of ideal diatomic gas gamma 7 by 5. Here gamma is the ratio of specific heats at constant pressure and constant volume of an ideal gas. The gas mixture does a work of 66 joule when heated at constant pressure. The change in its internal energy is. So we have to find out change in internal energy, and for that, okay, so we start with our work done by using ideal gas law. Work done is equal to P delta V because it is at constant pressure. So we can say work done, that is our W, is equal to P delta V, or we can write this as NR times delta T, and N is our total number of moles. So N is our total number of moles, which comes as 2 plus 1 is equal to 3. Therefore, we have that our work done is equal to 3R times delta T, and mixture is said to be 66 of work. Therefore we can say that our 66 is equal to 3R delta of T, which gives us this 66 goes by 22, and we get delta of T is equal to 22 upon R. Now we have to find out this change in internal energy. So you can say our change in internal energy, that is delta of U, is equal to our N C of V times delta T. Delta T we already found out. We need to find out our C of V, and this C of V is for our mixture. So let me write this as mixture, and we can write the formula that our C of V for our mixture will be equal to N1 for our first gas plus N2 for our second gas, N1 plus N2. And one is our monatomic, other one is our diatomic. Therefore C of V is going to change. So this comes as 2 multiplied by 3 by 2 times R plus 1 multiplied by 5 by 2 times R, and this comes as 1 plus 2. And here this 2 and 2 goes away. So we get this will be equal to 3, and this will be 6 plus 5, that is 11R, and divided by 6. So now we can easily find out our delta of U. So we can say our delta of U, N is our total number of moles. We have already stated it, and this is our 3 multiplied by of mixture, and change in temperature is our 22 upon R. Sorry, 22 upon R. So here this R and R goes away, and 3 goes by 2 and 2 goes by 22, and this comes as our 121 joules. So this is 121. Next question. So it was also asked in the advance 2023, and it states that an ideal gas is in thermodynamic equilibrium. The number of degrees of freedom of a molecule of a gas is n. The internal energy of 1 mole of gas is U of n, and speed of the sound in the gas is V of n. At a fixed temperature and pressure, which of the following is correct option? Okay, so we have to find out according to degree of freedom. In this option, the degree of freedom are basically 3, 5, 6 and 7. So we have to make a comparison between their respective velocities. Okay. So it means we have to make a comparison speed of sound and speed of and internal energy for different values of n. And as per the options, the value of n, it is our 3, 5, 6 and 7. So these are the various values of n that are given in the option. So we know that our internal energy which is our U, let us call this as U of n, is equal to n upon 2 times RT. And we have to remember here n is degree of freedom, and Next is speed of sound. Which is about V of n is equal to gamma RT upon m. And here our gamma is equal to 1 plus 2 upon n. Okay. So let us take the various values of n and find out all the respective. First of all, value of gamma we have to find out. So we can say that our value of n is equal to 3 and value of gamma will be equal to 1 plus 2 upon 3, giving us 5.3. And here u of n we can calculate directly. So we can say our u of 3 will be equal to, this comes as n is 5 by 3, so this will be coming as 5 by, sorry, 1 second, yeah. So u of 3 will be equal to our, 1 second, at a fixed temperature and pressure. Okay. Therefore, we can write that our u of 3 is equal to 3 by 2 times RT. And V of 3 will be equal to, gamma is our 5 by 3, so this comes as 5 by 3 and times m and its square root. Now let's solve it for n is equal to 5. So n is equal to 5, gamma is equal to 1 plus 5 by 3 is equal to 2 by n. So this comes as our 2 by 5, giving us 7 upon 5. So from here we get our u of 5. U of 5 is equal to, n is our 5 by 2 RT, and V of 5 will be equal to 7.5 times RT and times m and its square root. The next value of n is 6. So we can say value of n is equal to 6, giving us gamma is equal to 1 plus 2 by 6, which comes as 4 by 3. So u of 6 will be equal to 4 by 3 times RT, and V of 6 will be equal to, 1 second, this is u of 6 will be equal to 6 upon 2 RT, and V of 6 will be equal to 4 by 3 RT upon m square root. And finally we have our n is equal to 7. We get our gamma is equal to 1 plus 2 upon 7, which comes as 9 upon 7. We get our u of 7 will be equal to 7 by 2 RT, and V of 7 will be equal to 9 upon 7 RT upon m and its square root. Okay, so we can just, this will be coming as 3. So u of 6 will be equal to 6 RT, and first of all, let's make a comparison of our energy. So we have our U of 3 is equal to 3 by 2 RT, U of 5 is equal to 5 upon 2 RT, U of 6 is equal to 3 RT, and U of 7 is equal to 7.2 RT. And so this will be equal to our 3 by 2 is our 1.5, and this is our 2.5, this is our 3, and this is our 3.5. Okay. So this is arranged automatically in increasing order. So we get our, one second, U of 7, this is my U of 7, U of 6, U of 7 is greater than U of 6 is greater than U of 5 is greater than our U of 3. So let's check the option that are available. U of 3, this is incorrect, and this is also incorrect, and U of 7 is correct, and U of 7 is also greater than C of 6. Okay. So we have two options for our energy, that is U of 7 is greater than our U of 5, and second is our U of 7 is also greater than our U of 6. And now we come to our velocity. Okay, so for the velocity, rest of things will be same, so that will be 5 by 3, 7 by 5, 4 by 3, and 7 by 9. So two options are there. V of 5 is greater than V of 7. V of 5 is 7.5, and V of 7 is 9 upon 7. Okay, so this is the correct one. So we have option C is correct. So we have V of 5 is greater than V of 7. So we have a V of 5 is greater than V of 7. So therefore we get that our U of 7 is greater than U of 5. So this option, this combination is our correct one. So we get our option C is correct. C is correct. Next question. And it was also asked in the 2023 advance, and states that 1 mole of idle gas undergoes two different cyclic processes 1 and 2 as shown in the PV diagram. Cycle 1 processes A, B, C, D are isobaric, isothermal, isobaric, and isochoric respectively. In cycle 2, processes A prime, B prime, C prime, and D prime are isothermal, isochoric, isobaric, and isochoric respectively. The total work done during cycle 1 is W1 and cycle 2 is W2. The ratio of W1 to W2 is, okay, a basic figure is given to us. So we have 2 and they are representing different, you can say, okay. So let us, so this is our basically for the first part, which is more or less same. Second part is little bit typical. So for this is the first one, this is second, and this is for the third one. Okay. So let us start for our first one. We have to find out the total work done. And let us call this as our A, B, C and D. And let us call this as our P, Q, R and S. So we can write that our coordinate of A will be our 4 P0 V0. Coordinate B will be also our 4 P0, and the volume is here twice V0. And we have our C, the volume pressure is twice P0, volume is 4 V0. And then we have finally we have our D, which is our twice P0 and volume is our V0. Okay. And this is our process 1. Similarly, we can write for process 2, or let us solve first of all the process 1, then we come to process 2. And work done which is given as W1 will be equal to work done in the process for AB, for A, for B, for C and for our D. A is said to be our, A means from A to B is our constant pressure, which is isobaric. So we can say that our WA is isobaric, and this comes as our P delta V, and P is our 4 times P0, and pressure is our 2 V0 minus V0, which comes as 4 P0 V0. And then we come to our work done for B, and for our B is said to be our isothermal. So we can say it will be equal to our nRT, natural log of our we can write it like this. So WB will be equal to our integration of P dV, and so P we can write nRT integration of our dV, and the pressure varies from B to C. It goes from 2 V0 to 4 V0. Therefore we can say that our WP is equal to nRT, sorry, one second, this will be divided by V, and natural log of V, and this will be coming as our natural log of our 4 V0 upon twice V0, and this V0 V0, this goes by 2, so this comes as our nRT natural log of 2. And then we come to our C, and for our C it is once again ABC is of isobaric. So isobaric and isobaric is our P delta V, and pressure heat is 2 V naught, and it goes up from our V naught minus 4 V naught, and this comes as our minus 6 P naught V naught. And finally we have our WD, which is isochoric. Volume is constant, so we can say that work done is equal to 0. Now we can just substitute our total work done. And we get W1 will be equal to 4 P naught V naught plus WB. We can write this T in terms of P naught V naught, we can easily write. So let us keep like that only, because everything is P naught V naught. So we can write this as NR times 8 P naught V naught upon N times R, and natural log of 2 minus 6 P naught V naught and plus 0. So here this NR cancels out, therefore we get that our W1 is equal to, this is 4 P naught V naught and this is minus 6, so this comes as minus 2, so we get this as 8 P naught V naught natural log of 2 minus twice P naught V naught. So this is our W1. Similarly for process 2, that is our W2 is equal to WA prime plus WB prime plus WC prime plus WD prime. We can just write the formulas directly because it will be calculated more or less same, except minor variation will be in the values of pressure as well as our volume. So we can write WA will be equal to our nRT natural log of 2 V naught upon V naught plus 0 plus C will be equal to our P naught, and this comes as V naught minus twice V naught plus 0. 1 second. Yeah, there are two isochoric, so it's correct. And we get W2 is equal to, we can just substitute our temperature also. So this comes as NR. We get this as 4 P naught V naught upon NR, and natural log of 2 minus P naught V naught. NR cancels out, so we get the work done for the second is equal to, this is about 4 P naught V naught natural log of 2 minus P naught V naught. We have to find out the ratio, so that's quite easy now. So we can say our ratio, which is our W1 upon W2 is equal to, W1 is our 8 times P naught V naught, so this comes as 8 natural log of 2 minus 1 P naught V naught, and this comes as 4 natural log minus 1 natural log of 2 P naught V naught. P naught V naught cancels out, and we can can further solve it. This comes as our this will be our 2 raised to power 8, and okay, let me write it first of all. This comes as 8 natural log of 2 minus 1, and this is our 4 natural log of 2 minus 1. Okay. And we can write this one as, this will be written as 8 natural log of 2 minus, and I think I missed something. Okay, here it is 2. Yeah, that's why there was a problem. So this is our 2, 2, and this is our, okay, now it is easy. Otherwise we got stuck here. So we can take 2 as common, and we get this as our 4 natural log minus 1 natural log of 2 minus 1 divided by 4 natural log of 2 minus 1, and these two terms cancels out, so we get this ratio is equal to 2. Ratio of is 2. So this completes all the questions. Today we solved 21 questions. Of this, 17 were from the mains and 4 were from the advanced for the year 2023. So this completes all the 21 questions. Thank you.